So let's get started here. We're going to continue our discussion of these aldehydes and ketones. All right, and what we talked about was the functional group here, these carbonyl bonds, is going to be really important towards understanding the chemistry of these aldehydes and ketones. In particular, the fact that they got this polar bond, which leaves us with an electrophilic carbonyl carbon. Okay, and we're going to say that 1,000 times to drill it into our heads, that our carbonyl carbon is going to be playing the role of an electrophile. There's two things that make this a really good electrophile. One, it's in that polar bond, so it's got a bunch of electron density taken from it by that more electronegative oxygen atom. The other thing that's going to make this a particularly good electrophile is that if we have some nucleophile and we have our nucleophile attack that electrophilic carbonyl carbon, it's also got this pair of electrons that can act as a leaving group and jump up onto that oxygen atom so that that carbonyl carbon never has to break its octet. All right, so that's just a nice stable way of being an electrophile. Cool, so like we've seen before, we can use any variety of nucleophiles to react with our electrophile here. All right, so we've kind of looked at these categories before. All right, we have basic nucleophiles. And these all look like nucleophiles because they have a net negative charge. So for example, a hydroxide ion, a good nucleophile, we have a lot of electron density on that negatively charged oxygen. So that would be a good basic nucleophile. Or instead of a hydroxide ion, we can use an alkoxide ion. Again, that oxygen with a negative charge. All right, like oxygen, same family, sulfur can have that net negative charge. Sulfur is just a really good nucleophile because it doesn't have any basic tendencies at all. And likewise, we can have a deprotonated thiol. All right, we've looked at some nitrogen nucleophiles as well under basic conditions. In theory, that definitely does work. In practice, deprotonating a nitrogen is kind of a big pain in my butt. I've never seen it in the wild in my life, right? I know these bases exist. I know people do it somewhere, and you have ridiculous protective equipment in place because it's very, very dangerous. I've never personally seen it, right? So they exist, but like practically speaking, not so much. And what we'll see is we're going to throw them in a different category that is more practical. So I'm going to leave out nitrogen for right now, okay? Other basic nucleophiles that we've seen are carbon nucleophiles, and these are kind of a special category here. We have that one stable carbanion, that cyanide ion, kind of a special case. All right, the one that we've seen quite a bit, and it's very important because it's way more flexible, are those Grignards. Right, remember, in your Grignard, your carbon has a bunch of negative charge because it's able to steal that electron density away from that metal. Okay. The other category that we're going to put here is our hydrides, our lithium aluminum hydride, and the sodium borohydride. These would be hydrogen nucleophiles. All right, so under basic conditions, we can use oxygen as a nucleophile, oxygen with that net negative charge. We could also use sulfur nucleophiles. We got a few carbon nucleophiles that we can use. And then lastly, our hydrides are hydrogen behaving as a nucleophile. All of these nucleophiles, we can react with that good electrophile, that aldehyde or ketone. All right, a few of these we can also use under acidic conditions. All right, these nucleophiles aren't as strong of nucleophiles, but when we use acidic conditions, we're going to see that we turn our aldehyde or ketone into an even better electrophile, so we can get away with using these weaker nucleophiles. We have some oxygen nucleophiles that we can use under acidic conditions. And unlike our basic condition oxygen nucleophiles, these will not have net negative charge. So it's just going to be the neutral version of each of those oxygen nucleophiles we've already looked at, right? If I protonate a hydroxide ion, I get water. Likewise, if I protonate an alkoxide ion, I get an alcohol. Sulfur, also a good neutral nucleophile. Or our thiol. All right, under acidic conditions though, carbon is no longer going to be a good nucleophile. You just can't have Grignards in acidic conditions. They will react with that acid, all right? Likewise, you can't have a carbon cyanide ion under acidic conditions. So carbon's no longer a good nucleophile when it's neutral. It doesn't have any lone pairs when it's neutral, right? So it can't play the role of a nucleophile. Likewise, our hydrides don't survive under acidic conditions. We do have one category under acidic conditions that we don't see under basic conditions, and those are our halogens. Right? These halide ions are kind of odd in that they have negative charges, but are just such terrible bases that you can actually have them under acidic conditions as well. All right? Your hydrohalogens, hydrochloric acid, hydrobromic acid, hydroiodic acid, all very, very strong acids that will yield these negatively charged ions, right? So these are the only negatively charged ions that are compatible under acidic conditions. And since they are negatively charged, they are good nucleophiles. All right, so again, we're going to see we have these carbonyl carbons in our aldehydes and ketones. They play the role of electrophiles because they're in that polar bond with oxygen and they have that good leaving group. And since they're such good electrophiles, we can react them with a variety of nucleophiles. All right, some of which we've seen before, others are going to be kind of new to us here. Let's pick one that we've done before. Let's do our Grignard. This is a reaction that we covered last chapter as a way to prepare alcohols. All right, so let's take our butanone and we're going to react this with a Grignard. All right, everybody take a second and tell me my product of this reaction, and then we're going to look at our mechanism. Okay, my reagent list isn't quite complete here. We first react with that basic nucleophile, that Grignard, all right, but then there's this second step after we've already used our nucleophile. We do this, what's called acidic workup. We add in some weak acid, and that's what finishes off our reaction. All right, to be clear, we consider the Grignard a basic nucleophile. That acid is not present when that Grignard is in there. It's afterwards. It's a separate step in our mechanism. All right, so we're going to be attaching our carbonyl carbon to the carbon that's bound to the magnesium in my Grignard. All right, so here's my blue carbon. It's got a methyl group on one side, 2 carbons on the other side, and now I have my new carbon bond to that red carbon. All right, so we prepare an alcohol with a new carbon-carbon bond using our Grignard. If we're going to do our mechanism, the first step is that nucleophilic attack. My nucleophile attacking that electrophilic carbonyl carbon, and we kick that pair of electrons onto that oxygen atom. All right, at this point, our oxygen has accepted that pair of electrons, so we have that negative charge. Okay, just to keep my coloring consistent. My electrophilic carbonyl carbon and my nucleophilic Grignard carbon. Okay, this intermediate we see a bunch, and we're going to see it a whole lot more moving forward. And we're going to give it a name here. This is what we call our tetrahedral intermediate. All right. We call it that because our aldehydes and ketones about that carbonyl carbon, these are trigonal planar. Another reason, we can add that to our list here. Another reason it's such a good electrophile is it's got that trigonal planar geometry. Very easily accessible because it's just flat. All right, and our tetrahedral intermediate is stuck here. The only thing that we can do is use that acidic workup step. You can use water as well. They tend to add in weak acid and to protonate that oxygen. All right, so our electrophilic carbonyl carbon gets attacked by our nucleophile. We get this tetrahedral intermediate. And then we protonate that oxygen, that negatively charged oxygen, to get our final product, our alcohol. All right, so this would have been a reaction that we learned in our preparation for alcohols chapter. Okay, let's look at another one that's going to be a little bit less familiar, but has the same basic idea. Keep that same aldehyde or ketone. All right, and now we're going to use hydroxide with our aldehyde or ketone. Okay, take a second and see if you can't work through what the product of this reaction would be based on what we just did. right, so just like before, our nucleophile is going to attack that electrophilic carbonyl carbon. And we're going to, again, get that tetrahedral intermediate. All right. At this point, we're stuck with that alkoxide ion with its negative charge. So just like before, we're going to need a proton donor. With your Grignards, you do this second step, this acidic workup. Under basic conditions, in this case using this particular nucleophile, the hydroxide ion, we're going to do this under aqueous conditions here. So we got another water molecule, we got water molecules floating around. And that will be our proton donors under basic conditions. All right. And so we have this product here with these two hydroxyl groups on that same carbon. These things are what are called gem diols. All right, they are always forming in solution, in any aqueous solution actually. They are very difficult to isolate to get into high amounts unless you have a very, very tiny aldehyde or ketone. The equilibrium tends to lie in favor of that reactant side. Not a super favorable reaction, which is why you don't see them very often. But nonetheless, this reaction is always occurring in a small amount in any solution. So it's not like you don't form any gem diol at all. It's just the reaction's going both directions at the same time, and that equilibrium lies in favor of your aldehyde or ketone. In general, for our basic conditions, here we said we were going to use aqueous conditions. All right, we've talked about this before, our strategy for our proton donor under aqueous conditions. Whatever nucleophile you're using, you want to try to use the protonated version of that nucleophile as your proton donor, right? So your neutral protonated nucleophile, and that will give you a reaction where your nucleophile is attached to what was formerly your carbonyl carbon, along with that OH from what was formerly your carbonyl oxygen. All right, so again, we have our nucleophile. The protonated nucleophile will play the role of the proton donor in our reaction mechanism. Cool. All right, so now let's start looking at some of our other nucleophiles. Let's look at our acidic condition nucleophiles here. We'll switch up our aldehyde or ketone here for the fun of it. Everybody take a second and name this molecule for me. Okay, this would be cyclohexanone. Right, it's a ketone, so it has that -one ending. I don't have to say one cyclohexanone because wherever I put that carbonyl group, that would be carbon 1. All right, and now we're going to react this with another oxygen nucleophile, but this time we're going to use our acidic conditions oxygen nucleophile water. Okay. So let's try to do our mechanism here. At first step, our nucleophile is going to attack. We're going to get our tetrahedral intermediate. All right, what's wrong with our intermediate here? Somebody said it. I got a negative charge. I can't have this super strong base, an alkoxide ion, under acidic conditions. So that can't be the first step in my mechanism, that nucleophilic attack. So instead, how do we deal with our charges? All right, so we said this before. How do we manage charges in our mechanism? We're going to do a proton transfer step. All right, so if I'm under acidic conditions here, we can assume we have a bunch of hydronium ions floating around. And the first step isn't going to be nucleophilic attack, but rather I'm going to have to protonate that carbonyl oxygen. Okay, so now I have a protonated ketone here. All right, this serves two important points here. Number one, in our mechanism, we don't break any rules. We don't have any strong bases in an acidic mechanism, okay? The second thing, and most importantly for the reaction here, is this will actually turn that carbonyl carbon into an even better nucleophile, or I'm sorry, an even better electrophile. Because now that oxygen's protonated and it's really mad, so it's going to be able to pull electron density away from that carbon atom even more. So now we have our carbon atom here, our carbonyl carbon, that's an even better nucleophile, or geez Louise, better electrophile. Which is how we can get away with using our weaker neutral nucleophiles under acidic conditions. Now my water is going to attack. I'm again going to bring that pair of electrons up onto that oxygen to create our tetrahedral intermediate. All right, but importantly now my tetrahedral intermediate is not breaking any rules. Okay. Importantly, since water attacked, I still got that additional hydrogen on that other oxygen. All right, at the end of the day, we're again going to create that same product that we did using hydroxide. We're again going to get a gem diol. But we need one more step to do it. Everybody, based on what we've discussed about these acidic conditions mechanisms here, See if you can't finish this off. You're going to need a base. What base should you be using under acidic conditions? Anybody, what's my base going to be? Water. All right, and what I want you to do is just to compare what we did previously under basic conditions. We did the exact same thing, reacting a ketone with this oxygen nucleophile and forming our gemdiol, to what we just saw under acidic conditions. And what you'll note is that there's an extra step in this mechanism here, right? Why is there this extra step here? Well, we had to manage our charges by doing these proton transfers. And that'll be pretty typical. Your acidic mechanisms usually have a few extra proton transfer steps. And again, what you'll see, your goal, pencil and paper wise here with those extra steps, is to manage your charges so you don't have any negatively charged oxygens, for example, in your mechanism. Cool. All right. All right, I want you all to do one more on your own here. We're going to use that strong acid, hydrobromic acid. All right, and see if you can't tell me what our or see if you can't draw the mechanism to get from reactants to products here. All right, if you used hydronium as your proton donor, that'd be perfectly fine as well. I'm just going to use the HBr since it's right here. All right, but again, that first step is going to be to protonate that carbonyl oxygen. Since we're under acidic conditions, this will help us manage our charges so that when my nucleophile, my bromide ion, attacks, that tetrahedral intermediate doesn't have any positive charges. I'm sorry, doesn't have any negative charges. All right, and we get that nucleophile attached to what was formerly our carbonyl carbon. All right. One more thing we want to say about these reactions. We have an aldehyde or ketone. All right, you don't have to do the full mechanism here. Everybody just take a second and see if you can't guess what my product is going to be here when we react an aldehyde or ketone with an alcohol. If I'm reacting it with this neutral alcohol here, would that be acidic or basic conditions? Acidic. It won't react under just neutral conditions. We need it to have acidic conditions, so our electrophilic carbonyl carbon is an even better electrophile. So we have that oxygen from our nucleophile attached to that carbonyl carbon. Okay, this reaction tends to have sort of an outsized role in organic chemistry because it's very important in biochemistry. This is how your body links up sugars together to create starches. That's how it stores energy. So we have special names here. This is what's called a hemiacetal. And this one will actually react with yet another alcohol molecule. So if we have an excess of that alcohol, it will react one more time to form not a hemiacetal, but a full acetal. Where not one, but two alcohols are attached to what was formerly your carbonyl carbon. Okay, so we're going to do the mechanism for this second step here. Let me be good and put in my missing lone pairs. All right, if we're going to play the spot the difference game here, what bond am I going to need to break in that hemiacetal? All right, to be clear, if I'm going to color my carbonyl oxygen, that was my hydroxyl group here. The other oxygen came from my alcohol. So when I added my second addition of my alcohol, I've gotten rid of what was formerly that carbonyl oxygen. So I'm going to need to break this bond right here, and I'm going to need to form this new carbon-oxygen bond. All right, again, we're under acidic conditions. I need to break this hydroxyl carbon bond here. Remember, these hydroxyl groups are not good leaving groups. They're kind of hard to get off. But we had this common method that we used under acidic conditions to get rid of them, and that was to protonate them to make them a better leaving group. And so that's what's going to happen here. We have our hydronium under acidic conditions. We're going to protonate that hydroxyl group. Okay, so now where do we go from here? What is it that kicks off that leaving group? This is probably one of the more surprising mechanism steps. What is the impetus for kicking off that leaving group? Where does that come from? Well, this carbon, this tetrahedral carbon is kind of all blocked up. It's hard for a nucleophile to get there to just kick off that leaving group. It's actually this pair of electrons on that oxygen that comes back down and kicks off that leaving group. So everybody take a second and draw me my product here of this step. Right, so just following my electron pushing arrows here. When that pair of electrons on that oxygen comes down, it forms a carbon-oxygen double bond. All right, now that my oxygen has 3 bonds and 1 lone pair, it's going to have that formal charge of +1. Oh, I forgot a carbon, I'm sorry. All right, so now we're going to need that second molecule of ethanol. All right, make a little bit more room. Okay, see if you can't figure out how to finish this mechanism here. We're at this step. Get me to that acetyl. All right, so my other alcohol is going to play the role of the nucleophile attacking that kind of carbonyl-ish carbon. It's not technically a carbonyl carbon, but carbon-oxygen double bond here. All right, I still will have that hydrogen from my alcohol nucleophile that I got to get rid of, so we need to do one last proton transfer step. I'm going to use water. You could have used an alcohol, that ethanol as well. Oops. I need to do one last proton transfer step in order to get to my acetyl here. All right, so again, this is an important reaction in biochemistry, the formation of these hemiacetyls and acetyls. Carbohydrates have a bunch of hydroxyl groups as well as either an aldehyde or a ketone, and so your body can link them together for storage using these reactions here. All right, kind of the weird thing being this first step we got based on what we've done with all of our other nucleophiles. Turns out that you can add yet one more of your alcohol groups to create this acetyl here. Cool. All right. We'll call it there. We'll pick up with this next time. I don't want to dive into something and then rush it here. Cool. We got a few more discussions to go. One nucleophile, notably, that we left out was our nitrogen nucleophiles, and we'll pick up with that next time as well. Cool. Well, yeah, so you, in the next 2 days, are you going to be able to take it?
Yeah.
Okay, then I'll set it up then for either tomorrow or Wednesday.
Okay, so good. Thank you.